Based on what you were describing, this could soon be the biggest story in the world. Literally the biggest story in the universe.
Something extraordinary just happened, and if you're not paying attention, you're missing one of the most significant scientific events of the decade. Right now, an object from another star system is racing through our solar system, and in just the last 10 days, scientists have released the most detailed, the most comprehensive, the crispest visualization we've ever captured of an interstellar visitor. But here's where things get absolutely fascinating. The images reveal details that have Harvard astrophysicists questioning everything we thought we knew about comets, and NASA scrambling to explain behaviors that frankly don't quite add up. Think about that for a moment. We're witnessing something that traveled potentially billions of years through the void of space, and it's happening right now in real time, and what these new visualizations show is sending shockwaves through the scientific community. But before we dive into what makes these images so revolutionary, and why some scientists are privately losing sleep over what they're seeing, make sure you hit that subscribe button and turn on notifications. This story is developing literally by the day, and you don't want to miss what comes next. And if you find this as mind-blowing as I do, smash that like button, because what I'm about to show you will change how you see our place in the cosmos. November 19, 2025, NASA did something they almost never do. They held an emergency press conference, bringing together data from more than 20 spacecraft scattered across our solar system, all focused on a single object. The object is called 3I Atlas, and that designation alone tells you something remarkable. The 3I means it's only the third confirmed interstellar object ever detected passing through our cosmic neighborhood. The first was Oumuamua in 2017, the second was Comet Borisov in 2019, and now we have this. But 3I Atlas is different. It's bigger, it's brighter, and the visualization that NASA's team just delivered represents the most comprehensive observational campaign ever mounted for an object from beyond our solar system. Tom Statler, NASA's lead scientist for solar system small bodies, described the unprecedented coordination at that press conference. He said tracking 3I Atlas was like watching a baseball game from different seats around the stadium, with dozens of spacecraft each holding different cameras, trying to capture the same fast-moving target. Nobody had the perfect view, but together they assembled something unprecedented. The result is what we're calling the crispest visualization of an interstellar object in human history. Let's talk about what these images actually show, because the details are stunning. The Mars Reconnaissance Orbiter, positioned on the favorable side of the Sun while Earth-based telescopes couldn't see the comet at all, captured images from 90 million miles away showing a fuzzy white coma of dust and ice surrounding the nucleus. But it's the MAVEN orbiter's contribution that really catches your attention. From 20 million miles away, MAVEN detected what scientists call science wiggles in the ultraviolet spectrum. These are signatures of hydrogen gas being released as sunlight vaporizes water ice from the comet's surface. Think about what that means. We're detecting individual molecules of water, frozen for potentially billions of years in interstellar space, now evaporating in the heat of our sun. The James Webb Space Telescope added infrared observations, revealing the chemical composition in unprecedented detail. And here's where things get weird. Webb detected a carbon dioxide to water ice ratio that's significantly higher than what we see in comets born in our solar system. Not just a little higher. We're talking about a composition that doesn't match anything in our cosmic backyard. But the real showstopper in this visualization comes from NASA's Punch mission. That's the polarimeter to unify the corona and heliosphere, a relatively new spacecraft that launched earlier this year. Punch observed 3I Atlas continuously from September 20th through October 3rd, capturing the comet's tail structure as it passed behind the Sun. What Punch revealed is extraordinary. The images show a complex tail structure extending hundreds of thousands of kilometers into space, with details so crisp you can see individual streamers and jets emanating from the nucleus. These aren't artist impressions. These are actual photographs, processed and combined to create a visualization that lets us see, for the first time, the three-dimensional structure of an interstellar comet's tail. When you stack Punch's data with observations from the Lucy spacecraft, which photographed the coma from 240 million miles away in the opposite direction, scientists could literally reconstruct how dust and gas flow off this object in 3 dimensions. That's never been done before with an interstellar visitor. Now here's where the story takes a dramatic turn, because not everyone agrees on what this visualization is actually showing us. On November 8th, just 11 days before NASA's press conference, a team of astronomers including Michael Yeager, Gerald Remen, and Ernesto Prosperi captured their own deep images of 3I Atlas at 4.10 Universal Time. What they saw stopped them in their tracks. Stacked images, combining 24 exposures in the green filter plus red and blue filters, revealed at least 7 distinct jets emanating from the comet. But here's what makes this particularly intriguing. Several of those jets are what astronomers call anti-tails, meaning they're pointing toward the Sun, not away from it. That's not normal behavior, that's something else entirely. Harvard astrophysicist Avi Loeb analyzed these images and immediately published his findings. His conclusion: The jet structure is so complex and so unusual that it raises fundamental questions about what 3I Atlas actually is. Think about how a normal comet behaves. When ice on the surface gets heated by sunlight, it vaporizes, creating jets of gas and dust that push away from the sun. The pressure from those jets can actually change the comet's trajectory slightly, creating what's called a non-gravitational acceleration. Scientists measure this all the time with regular comets. For 3I Atlas, astronomers measured a non-gravitational acceleration of 5 times 10 to the minus 7 astronomical units per day squared during its closest approach to the Sun, which occurred around October 30, 2025. That number might sound abstract, so let me translate it. This acceleration changed 3I Atlas's trajectory by about 0.1 million kilometers over the course of a month. Now, that might not sound like much, but consider this. The comet passed within 1.4 astronomical units of the Sun. That's about 130 million miles just inside the orbit of Mars. The gravitational forces at play are enormous. Any deviation from a purely gravitational trajectory tells us that mass is being ejected from the object, and here's where the numbers don't quite add up. To generate the observed non-gravitational acceleration with the jet pattern visible in these crisp new visualizations, Loeb calculated that 3I Atlas would need to eject a substantial fraction of its total mass near perihelion, not just a little bit of ice and dust. We're talking about potentially 10 to 20% or more of the entire object being blown off into space, and that creates a physics problem. If 3I Atlas shed that much mass, its nucleus should have shrunk noticeably. Scientists should see fragmentation, brightening from exposed fresh ice, changes in the rotation rate as mass distribution shifted. The Hubble Space Telescope, observing from 277 million miles away on July 21st, estimated that the nucleus diameter falls somewhere between 1,400 feet and 3.5 miles. That's a huge range, admittedly, but even at the upper end, losing 20% of your mass is a big deal. Yet the comet's behavior remained remarkably consistent through perihelion. The rotation period stays at approximately 16 hours. No major fragmentation events have been observed. The brightness curve follows predicted patterns for steady outgassing. So how do you explain 7 distinct jets, including antitails, without corresponding changes in the nucleus? If you're still with me, go ahead and hit that like button, because what I'm about to tell you next gets even stranger. On November 23rd, just 6 days ago, Avi Loeb published another analysis that sent ripples through the astronomy community. He focused on a specific number, 53.445 million kilometers. That's the minimum distance that 3I Atlas will reach from Jupiter when it passes through the outer solar system on March 16, 2026. Now you might think that's just a random distance, determined by the comet's trajectory and Jupiter's position. But Loeb noticed something remarkable. Jupiter has what's called a Hill radius, which is essentially the region of space where Jupiter's gravity dominates over the Sun's gravity. It's the zone where Jupiter can hold onto orbiting satellites without the Sun ripping them away. The Lagrange points, those famous equilibrium points where gravitational forces balance out, sit right at the edge of the Hill radius. On March 16, 2026, given Jupiter's distance from the Sun on that specific date, the Hill radius calculates to 53.502 million kilometers. You see it, the minimum approach distance is 53.445 million kilometers. The Hill radius is 53.502 million kilometers. They match within 0.06 million kilometers. That's a margin of error of 1 part in 1,000. But when you consider the full diameter of Jupiter's orbit around the Sun, this coincidence amounts to 1 part in 26,000. And here's what makes this statistical improbability even more intriguing. The measured non-gravitational acceleration that 3I Atlas experienced near perihelion, the acceleration we just talked about that's visible in those stunning jet visualizations, that acceleration changed the comet's minimum Jupiter distance by exactly 0.1 million kilometers. In other words, without that course correction near the Sun, 3I Atlas would have missed Jupiter's Hill radius. With the course correction, it arrives precisely at the edge of Jupiter's gravitational sphere of influence. Loeb poses the question directly, is this a coincidence or is this object fine-tuning its trajectory? Let's zoom out for a moment and look at the bigger picture of what these crisp new visualizations are revealing. The James Webb Space Telescope's observations from August 6 showed something that no one expected. Webb detected not just carbon dioxide and water, but specific molecular signatures that don't match solar system comets. The carbon dioxide to water ratio is anomalously high. There's also gas unusually rich in nickel relative to iron. The James Clerk Maxwell Telescope, observing on September 7 when the comet was 2.33 astronomical units from the Sun, detected hydrogen cyanide, which is common in comets, but in proportions that again raise eyebrows. Every measurement seems to tell us that 3I Atlas formed in a very different environment from our local comets. Tom Statler in that NASA press conference said that circumstantial evidence points to the comet originating in a very old planetary system, possibly one older than our own solar system. Think about that. This object may carry chemical signatures from a star system that formed billions of years before Earth existed. But what makes this particularly compelling is the dust behavior. Scientists noticed something unusual in the Punch and SOHO visualizations. When 3I Atlas first approached perihelion, dust was initially blown toward the sunward side. That's backwards from what you'd expect. Solar radiation pressure should push dust away from the sun, not toward it. Eventually, the pressure did push the dust back into a more normal tail configuration, but this took longer than it should have. The dust grains around 3I Atlas appear to have different properties, different sizes, different compositions than what we're used to seeing in our solar system's comets. And when you combine that with the 7 distinct jets visible in those November 8th images, some of which are firing in the sunward direction, you're left with a picture that doesn't quite fit the textbook definition of a comet. Now NASA is absolutely clear in their position. Nikki Fox, the Associate Administrator of NASA's Science Mission Directorate, stated unequivocally at the November 19th press conference, "This object is a comet. It looks and behaves like a comet, and all evidence points to it being a comet." She emphasized that none of NASA's observations show any technosignatures or anything that would lead them to believe it's anything other than a natural object. And she stressed that 3I Atlas poses no threat to Earth, as it will come no closer than 170 million miles to our planet. Scientists are confident that all objects in our solar system will be just fine as this visitor passes through. But here's where the scientific debate gets interesting. Avi Loeb isn't claiming definitively that 3I Atlas is artificial. What he's saying is that the anomalies are worth investigating, and that we shouldn't dismiss possibilities just because they sound extraordinary. He points to the complex jet structure, the trajectory that appears to aim for Jupiter's Hill radius, the unusual composition, the anomalous dust behavior, and the fact that the comet maintains structural integrity despite apparently ejecting enormous amounts of mass. Each individual anomaly might have a natural explanation. But when you stack them all together, Loeb argues, the probability space becomes uncomfortably small. There's another layer to this that makes the timing particularly interesting. During the 43-day government shutdown that lasted through October and early November, NASA couldn't comment on 3I Atlas or release new images. The silence created a vacuum that social media filled with speculation. When Elon Musk suggested on a podcast that something beyond gravity might be influencing the comet's motion, and when Kim Kardashian posted on social media asking NASA to spill the tea on the object, the story went viral. By the time NASA held their November 19th press conference, there was enormous public pressure for answers. And what they delivered was that unprecedented visualization combining data from more than 20 spacecraft. It's the most comprehensive portrait ever assembled of an interstellar object, showing us details that were literally impossible to see with earlier visitors like Oumuamua and Borisov. So what happens next? That's where things get really exciting because we're entering a critical observation window. Right now, as of late November 2025, 3I Atlas is in the constellation Virgo, traveling at speeds up to 250,000 kilometers per hour. It's currently about 292 million kilometers from Earth, which makes it visible through telescopes but not to the naked eye. Its apparent magnitude is around 10, which means amateur astronomers with decent equipment can observe it from dark sky locations. On December 19th, just 3 weeks from now, 3I Atlas will reach its closest approach to Earth at 170 million miles. That's almost twice the Earth-Sun distance, so there's zero danger, but it represents our best opportunity for detailed ground-based observations. Every major observatory on the planet will be pointed at this object. We'll get spectroscopy data, light curve analysis, and potentially even radar observations if the geometry works out. But the real moment of truth comes on March 16, 2026. That's when 3I Atlas reaches its minimum distance from Jupiter. NASA's Juno spacecraft, currently in orbit around Jupiter, will have an unprecedented opportunity to observe whether anything unusual happens during this encounter. If Loeb's calculations are correct, and the comet genuinely did fine-tune its trajectory to reach Jupiter's Hill radius, then we might observe course corrections, object deployment, or other behaviors that would be impossible to explain as natural phenomena. If nothing unusual happens and 3I Atlas simply coasts past Jupiter following Newtonian mechanics, that would strongly support the natural comet explanation, and suggest that the Hill radius coincidence is exactly that, just a coincidence. Either way, we'll know more in less than 4 months. After the Jupiter encounter, 3I Atlas will continue outward, crossing the orbit of Saturn and eventually leaving our solar system entirely. Because its orbit is hyperbolic with an eccentricity of 6.2, it's not gravitationally bound to the Sun. It's just passing through, a messenger from another stellar system, briefly visible to us before it vanishes back into the interstellar void. And that's what makes this moment so precious. The crisp visualizations that NASA and independent astronomers have captured over the past few months represent something that won't happen again for potentially decades. We don't get interstellar visitors very often. Oumuamua came and went before we could study it properly. Borisov gave us more time but never got this close. 3i Atlas is giving us the best opportunity yet to understand what exists beyond our solar system, to sample material from alien star systems, to test our physics against objects that formed under different conditions. The chemical data alone is revolutionary. The high carbon dioxide to water ratio suggests that 3i Atlas formed in a region exposed to more intense radiation than our solar system's Oort cloud, possibly around an older, hotter star. The nickel-rich gas could indicate a different mix of heavy elements in its parent system, which would tell us about the chemical evolution of that system's host galaxy. When our sun formed 4.6 billion years ago, it inherited elements from previous generations of stars that had lived, died, and scattered their enriched material into the interstellar medium. 3i Atlas might contain elements from even earlier stellar generations, a chemical fossil from the ancient universe. Every measurement we take, every spectrum we capture, every image in that comprehensive visualization is a window into cosmic history that predates Earth itself. And that brings us back to the central question that these crisp visualizations have made impossible to ignore. Is 3i Atlas a natural comet from an old, distant planetary system, carrying ice and rock that formed billions of years ago? Or is it something else, something that's using those jets not for passive outgassing but for active course corrections? The honest answer is we don't know, and that's what makes this so exciting. We're living through a historic moment in astronomy. For the first time, we have the technology, the coordination, and the observational capacity to truly study an interstellar object. The visualization that NASA delivered on November 19th, combining data from spacecraft scattered across millions of miles, from Mars orbit to the asteroid belt to Earth orbit and beyond, represents a new era in space science. We're no longer limited to passive observation from a single vantage point. We can surround these objects, study them from multiple angles in multiple wavelengths, and build a three-dimensional picture of what's actually happening. Whatever we learn about 3i Atlas will inform how we search for and study future interstellar visitors. And those visitors are coming. Statistical models predict that at any given time there are thousands of interstellar objects passing through our solar system. Most are too small or too dim to detect. But as our survey telescopes get better, as our coordination improves, as our visualization techniques become more sophisticated, we'll catch more of them. The Vera Rubin Observatory, scheduled to begin operations soon, will revolutionize our ability to detect these objects. We'll go from finding one interstellar visitor every few years to potentially discovering dozens annually. And each one will carry information from another stellar system, another epoch of cosmic history, expanding our understanding of how diverse planetary systems can be. So where does that leave us today? We have the crispest, most detailed visualization ever captured of an interstellar object. We have measurements showing unusual composition, complex jet structures, and a trajectory that some scientists find suspiciously precise. We have a natural explanation that fits most of the data, and we have alternative hypotheses that can't quite be ruled out. We have 3 weeks until closest approach to Earth and 4 months until the Jupiter encounter. The data is still being analyzed, papers are being written, telescopes are being reserved for follow-up observations. This is real exploration, real discovery happening in real time. The story of 3i Atlas is far from over. Every day brings new images, new measurements, new insights into this visitor from beyond our solar system. Make sure you're subscribed with notifications turned on, because as this story develops over the coming weeks and months, you'll want to be among the first to know what scientists discover. Drop a comment below with your thoughts. Do you think 3i Atlas is a natural comet with some unusual but explainable properties? Or do you think the anomalies that Loeb and others have identified suggest we need to keep an open mind about alternative explanations? This is exactly the kind of mystery that reminds us how much we still don't understand about the universe. Remember to share this with anyone who loves space and science, because these moments don't come along often. An object from another star system is racing through our cosmic neighborhood right now, visible through telescopes, carrying secrets from billions of years ago. Whatever it is, wherever it came from, however it got here, the visualization we now have gives us an unprecedented window into the wider cosmos. These are the mysteries that remind us how vast and strange the universe really is, and how fortunate we are to be alive at a time when we can finally begin to explore it. Until next time, keep looking up.